Topic C, question 19, and this is again the additional HL content. So all the SL MCQs have already been covered, and this is just the additional HL MCQs that weren't covered. So definitely go check out the playlist, and questions like question 20 are there. So we have question 19, a mass oscillating vertically on a spring undergoes simple harmonic motion with amplitude x, total energy E, and maximum speed V max. What is correct about the elastic potential energy and speed V when displacement is x over 2? Okay, so we have E total is equal to E, right? And what is our formula for potential energy, elastic potential? We have half kx squared, right? And when x is equal to the amplitude, that is our total energy, right? Let's say we have a spring, let's just draw, and we have our mass. When it is, let's say, yeah, when it is at its amplitude, say this is its equilibrium, it has zero velocity, which means zero kinetic energy, right? So as E potential is max, right? EK is equal to 0. And so E total is equal to EP is equal to max. And so we have kx squared, right? We're going to use this amplitude x. And so our E is kx squared. But we also know that at x over 2 displacement, we're going to have kinetic energy as well that this potential energy was converted into, right? So now we have E potential at x over 2 is equal to half k x over 2 squared, and that is essentially 1/4 of half k x squared, right? And that is 1/4 E. And so now we can look here. Let's change this to H just for simplicity. And so EH is equal to 1/4 E is definitely less than E over 2. And so we can say this is correct and this is correct. Now we need to look at kinetic energy. So if our potential energy is 1/4 E, now let's find our kinetic energy. So EK is simply going to be E total, right, minus our E potential. And so what we have is half mv squared is equal to E minus E over 2, right? Or let's see. Yeah, we can do it like that. But we want this in terms of V max. Okay, so V max. So E total is also going to be half mv max squared, right? And that is when we're at this equilibrium point. So V max is here, or EK max. Right? And so what we have is equal to half m. We have E total half mv max squared minus EH is 1/4 of E, right? And so we have let me just write this here. Yep. And so we have half 1/4 of half mv squared max, right? And so we can say half mv squared. We can remove that from everywhere, right? Cancel those out, and we get v max squared minus 1/4 v max squared. And so we get v squared is equal to 3/4 v max squared. And so v is equal to square root of 3/4 v max, which is roughly equivalent to, let's check a calculator, root 3/4, roughly 0.866 v max. And so we can easily tell from this our v is greater than v max divided by 2, right? Or v is it's more than 0.5. So it has to be either of these. And so our answer is A. And let's move on to question 22, and this is C3. We have a double slit experiment using coherent light. Coherent means emitted with same phase difference, constant phase difference. Phase difference, or no phase difference, either way. And so the central bright fringe is observed on a screen at point P. Point of destructive interference occurs at point Q. So here is destructive, here's constructive. Only one point of constructive interference is observed between. Okay, so we have another peak, secondary maxima here. Okay, so we can draw a diagram. Oof. Right, and oops. Right, hopefully that's clear. And we have our central max, and we have a secondary max. This is not the best diagram. Definitely needs to be better. Right. Yep. Okay. And so they're asking what is the path difference at Q. Okay. So we have constructive interference, and since there's no phase difference that we saw here, there has to be a path difference if there's constructive interference. And so what we know is this is always 0. And this is lambda. This is lambda. And so from our phase difference and path difference formulas, we know that these are in half integer wavelengths. And so this would be 3/2 lambda. This would also be 3/2. Oh no, sorry. Half lambda. And this one, 3/2 lambda. Right? So this is the first order maxima, 0th order, first, and again, first. And this is the first order minima, or yeah. And so when they're saying what is the path difference at Q, we already know that it's 3/2 of the wavelength, because there must be one secondary maxima here, so it cannot be half because there's another minima right in between. Now we have question 23. Monochromatic coherent light, again the same thing, is directed normally at a diffraction grating with n slits per unit length, and we always need to remember this. D is equal to 1/n, and this is slit separation, and this is slit per unit length, and that's given. And so we have 9 maxima in intensity are produced on a screen far away. That's going to be important, I think. What change will occur to the angle between successive maxima and the number of observable maxima when n becomes 2n? Okay. So let's look at this. When we have a screen that's really far away, right? This is a diffraction grating. It can be treated as a single. And so we treat this as S, right? This is one maxima and this is the other maxima. We treat this as theta, and we can treat this as our distance because the screen is so far away that we can use a small angle approximation. And so essentially this distance d is roughly equivalent to this perpendicular distance, right? So actually this is d and this is L, right? And L is roughly equivalent to D. Let's write that here. L is roughly equivalent to D. And we know our arc length formula. We can use that as well to approximate. Arc length, S is equal to R theta, right? And here, R is L, which is roughly equivalent to D. So we say D theta. And we also have S is equal to lambda D over D, right, from our formula book. So what we can say is theta is equal to lambda over D, or let's just say roughly. How about we put this first? Roughly equivalent to D theta. And so we get this, right? This 2 cancels out. And so we can use this to estimate. Theta is thus roughly equivalent to lambda over n using this formula. Now that will give us the answer to our angle between successive maxima. If n increases, our angle must also increase. And so we have either of these. And now we have number of observable maxima. Now we have to use this. E sine theta. Right? And theta is the angle between successive maxima. So let's say max. So we can use our formula for, we can reorganize this just to write in terms of n, and we have a d, right? So our d becomes 1 over n, and we have lambda. And so what do we do now? We have n was 9, right? We had 9 maxima in intensity produced. Now we have 2n. So if n increases, number of maxima perceived decreases, right? And we can see this in the formula with n in the numerator, in the denominator. And so we can say n is going to decrease number of observable maxima. And what we need to remember is that when we're looking for the maximum number of observable maxima, we always use sine 90 is equal to 1 as our angle. But in this case, it doesn't really matter, as that acts as a constant. And so our answer is A. Now let's see if there's anything else. No. So that's it for topic C.